Next, we're going to take a look at the derivative of the arcsecant function. So we have no new vocabulary here and just the rule for the derivative of the arcsecant, also known as the inverse secant function. So we're going to begin this the same way we began the derivatives of the arcsine and the arctangent. We're going to start with the property of inverse functions. It says composing a function with its inverse yields the identity function. So in doing that, we will say that the secant of the inverse secant of x is equal to x. And then we will proceed with taking the derivative with respect to x of both sides of this equation as we've done before. So the secant derivative is, of course, two pieces. It's secant of the input, tangent of the input. So that's going to take a little bit more work than the previous two times we've done this. We're going to have secant of the inverse secant of x times the tangent of the inverse secant of x, and then times the derivative by chain rule of the inverse secant of x, and then this is equal to 1 on the right side. All right, the next thing we're going to do is divide by the secant of the inverse secant times the tangent of the inverse tangent, but in doing so, I also want to point out that secant of the inverse secant is x, except we're going to write that as absolute value of x, and this has to do with the domain and the range of the arcsecant function. This input could be both positive or negative input for x, and you can see that by looking at the graph of the inverse secant. So we're going to divide by that and this tangent of the secant inverse of x on both sides. So then we're going to divide here also by absolute value of x, and then tangent of the inverse secant of x. Okay, so now we almost have a rule. We've got the derivative with respect to x of the inverse secant of x is equal to 1 over the absolute value of x times the tangent of the inverse secant of x. So once more, let's take a look at a first quadrant triangle with an angle that is referred to by inverse secant of x. And we're thinking about that once more as x over 1. So if we go to our right triangle ratios, the secant is, of course, hypotenuse over adjacent. So that means the hypotenuse of this triangle is x and the adjacent side is 1. And then by the Pythagorean theorem, we would look at the opposite side to that angle as being the square root of x squared minus 1. So we're looking for the tangent of that angle, and we remember that tangent is opposite over adjacent. So the opposite side is root x squared minus 1. The adjacent side is 1. So we can replace tangent of inverse secant with just root x squared minus 1. And that means we have a rule for the derivative of the inverse secant as 1 over the absolute value of x times the square root of x squared minus 1. Or put more formally, the derivative of the arcsecant function is 1 over the absolute value of x, square root of x squared minus 1. And if the input to that function is not just x, if it's a function of x, in other words, u, then we have 1 over the absolute value of u times the square root of u minus 1, or we can call it u prime over that denominator, absolute value u, square root of u squared minus 1. So let's see this in action. We're going to use the formula to find the derivative of the inverse secant of 5x to the 4th. So this is going to be a 1 over the square root of that input to the inverse secant function squared. So this is a 5x to the 4th squared minus a 1, and then by chain rule times the derivative of 5x to the 4th. So that's 20x to the 3rd. So let's simplify a little bit more. We've got 20x to the 3rd over a square root of 5x to the 4th quantity squared. It's going to be 25x to the 8th minus 1, and we have our derivative. Now let's try exercise 17 from the text. It says find the derivative of y with respect to the appropriate variable. In this case, that variable is t. And here's our function, the inverse secant of 1 over t, where t is between 0 and 1. So the key takeaway from this is that t is positive. And so when we start thinking about the absolute value of t, we're going to be able to sort of ignore that piece since it's always going to be positive anyway. All right, so let's get on with the derivative. dy dt, derivative of y with respect to t, is going to be 1 over absolute value of 1 over t times the square root of 1 over t quantity squared minus 1, and then by the chain rule, times the derivative of 1 over t. And since 1 over t is t to the negative first, we can look at the derivative as being negative 1 over t squared, or that's negative 1 t to the negative second. All right, so now we want to simplify a little bit. So we know we're going to have a 1 over, we have this 1 over t. I'm going to take away the absolute value bar since we know that t is positive. And we have times the square root of a 1 over t quantity squared. So that's 1 over t squared minus a 1. But I'm going to rewrite that 1 since I'm going to try to perform the math inside the square root. I'm going to call that t squared over t squared. And you'll see why in a moment. It's because I need a common denominator to put those two pieces together. And this is times a negative 1 over a t squared. So let's continue the simplification process. 1 times a negative 1 in the numerator is just a negative 1. In the denominator, I have this 1 over t. I also have a t squared, so I'm going to multiply by that here. And then I have a square root of, once we have this common denominator, I can see that as a 1 minus a t squared over a t squared. And that's interesting to me because I know that the quotient of a radical is the same as the radical of the quotient. So that means I can actually think about this piece as being a square root of 1 minus t squared over a square root of t squared. And the square root of t squared is, of course, a t. So what does that mean for us? Well, this is a negative 1 on top. It's a 1 over t times a t squared times a square root of 1 minus t squared, and that's over a t because we have the square root of t squared. Well, all of those t's then in the denominator turn out to cancel and make 1 because we have 2 t's in the numerator, 2 t's in the denominator. They cancel, and finally that means we have an answer of negative 1 over the square root of 1 minus t squared. So that was some intense algebra there, going from step 2, 3 to 4 to a final answer. If we only needed to plug in a number, say this was a position function, we wanted the velocity at a certain time, generally you can keep this first dy dt, this first derivative, not simplify it at all, plug in the value that you need and work from there. But for this example, I did want to go all the way through the simplification process, and that's the derivative of the arcsecant.